Okay, ladies and gentlemen, we're going to be talking about solution stoichiometry today, acid-base neutralization reactions, and then we'll talk about some precipitation reactions in solution stoichiometry. But let's take a look at this here real quickly. And within our solutions, we can use our molarity formula. Molarity equals moles per liter. And that's really important because it allows us to take a look at moles. And so that's our big thing there. Stoichiometry, obviously, we're going to take a look at moles of whatever substance we have, and we can always convert that to moles of a different substance, usually another reactant in a solution stoichiometry problem, sometimes a product though. And from those, we can go down the road to grams of either one. And so these all kind of connect together, the moles in the solution stoichiometry here with the moles of A or moles of B or grams of A or grams of B. So let's take a look at how this all plays out in a problem. Okay, so what we have is how many grams of calcium hydroxide, a strong base, are needed to neutralize 25 milliliters of a 0.1 molar nitric acid solution, which is a strong acid. And probably the best place to start on any of these types of problems is we want to write a balanced equation. And I know we've been studying and looking at net ionic equations, and net ionic equations are definitely useful here. But we're going to write a complete equation as we're doing some stoichiometry. It just makes life a little bit easier for us. And so we have our calcium hydroxide, and we're going to react that with nitric acid. It's a neutralization problem with it, which is a double replacement reaction. The metals are going to switch places, hydrogen acting like the metal in the nitric acid. So calcium and hydrogen are going to switch places. So we're going to get calcium nitrate formed, and we're also going to get water made, just like that. And now we need to balance this guy out. So I'm going to put a 2 in front of that and a 2 in front of that. And that gives us our balanced equation. And that's a good place to start. Now, we're going to use this balanced equation to do a little bit, to write down some information here and what we're looking for. So we're looking for grams here is what we're looking for. And what we're given is we're given a 0.100 molar solution of the nitric acid, and we're given 25 milliliters of the nitric acid. Now, what we can do for that is we can use both of these givens, and we can use the molarity formula to calculate moles of the nitric acid. And once we know the moles of our nitric acid, we can use that to convert to moles of our calcium. Oops, let me put that 2 on the outside, of our calcium hydroxide. And then once we know moles of calcium hydroxide, we can easily convert the grams of calcium hydroxide. So let's go ahead and do that. And so let's take our molarity formula. Molarity equals moles per liter for the nitric acid. And we're going to solve this for moles. We're going to get moles equals molarity times liters. We're going to plug our values in here, and we have a 0.100 molar solution. We're going to multiply that by 25 milliliters, but we of course have to convert that to liters by dividing by 1,000 milliliters. And that's going to give us an answer of 0.0025 moles of the nitric acid. And that's an important value because we can use moles to convert, and we're going to do that over here on our next page. And so let's take that same number of moles, 0.0025 moles of our nitric acid solution, and let's go ahead and convert that to what we're looking for, which is grams of our calcium hydroxide. And so a moles to moles is we're going to use the mole ratio of calcium hydroxide from the balanced equation, which was 1 mole. And then we had 2 moles from our balanced equation there for our nitric acid. Once again, this is our mole ratio from our balanced equation. And then we're going to convert to grams of calcium hydroxide, and we have to multiply by the molar mass, which is 74.1 grams. So it's basically 74.1 times 0.0025 divided by 2, and I get 0.0926 grams of calcium hydroxide needed to neutralize that amount. And there we go. And that's how we do a solution stoichiometry problem. The next thing I want to talk about is you're going to see this come up in some of the questions we're going to be working on, and that's the idea of what a titration is. A titration, and basically what a titration is it's a method, a lab method that's used to find it's a method, a lab method used to find an amount of an ion or amount of a solid formed or something like that, or even a neutralization. That's what it is. Now, a couple of definitions that are going to go along with a titration, then I'll show you kind of do a quick drawing of what a titration is all about. Is you might see the wording standard solution, and this is going to be a solution that has a known molarity. We make this solution up knowing that it's going to be 2 molar or 5 molar or whatever it is. And we are going to take this and we're going to mix it with an unknown solution to try to figure out what that concentration is of the unknown solution. We might also come across the terminology of equivalence point. And what an equivalence point is going to be equal number of moles of each reactant. And so when we have an equivalence point of, let's say, in a neutralization reaction, we might have equal number of hydrogens and equal number of hydroxides. Once we reach that, we would be at our equivalence point, and we'd have nothing but water produced. So equal number of moles of our reactants is equivalence point. In a titration, we might also use an indicator. And an indicator is going to be a color-changing solution that lets us know we reach some equivalence point, or even what we call end point. A good example of that would be a chemical called phenolphthalein, which is going to turn pink with a base, and I'll show you a demonstration of this tomorrow in class. But that would be an indicator. Now, on our next page over here, what we're going to do is we're going to talk about kind of what a titration might look like. And so I'm going to kind of sketch something here. And so on a titration, what we'd have is, one, we'd have a ring stand. And instead of putting a ring on here, like if we were going to heat something up, we would use a clamp. And then we would attach to this clamp a device called a burette. And a burette's going to kind of look something like this. And on the burette, they kind of have a way to open and close and allow some chemicals to come out. There's also going to be increments going all the way down this burette. It's usually open on the top end. And we're going to be able to open and close this burette to allow some chemicals to slowly flow out. Down here below it, we might put a flask. And in the flask, we might put some unknown solution. And we would know how much we put in there. Maybe we'd say we put 20 milliliters in there. And up here in the burette, what we're going to put is we're going to put our standard solution. And what that's going to allow us to do is to drip into our unknown solution, a standard solution, which maybe if we added some indicator to this, we'd have some sort of color change that would occur. And the color change would let us know, or maybe we'd even put a pH meter in there or something like that, so we could track the pH. So that's kind of a general thing, and we'll probably do a lab this year where we'd actually use a burette and do a titration. So they're kind of interesting to do. But now you kind of know what we're talking about when we talk about titrations, and you'll see that come up with some problems here. Let's throw another type of problem at you now. Okay, so in this problem, we're going to do a titration involving some ions. So basically what we're looking for is what is the mass of the chloride ion in a solution that is, we have 20.2 milliliters, and we have a 0.10 molar of a silver ion present in solution, and we're going to react it with a chloride ion until it's all gone. And we'd have to put in some sort of indicator in here to let us know it's all gone. The net ionic equation, we're going to use the net ionic equation here, is going to be the silver ion reacts with the chloride ion, and both of these are in aqueous solutions, and they're going to form silver chloride, which is insoluble. It's going to form a white solid. We remember that chloride is typically soluble except for silver, mercury, and lead, so here's the time where it's with the silver. Okay, so let's analyze what we need to do here. We're looking for our mass of chloride, which is going to be in grams, and we're given, again, we're given our molarity as 0.100 molar of our silver ion, and we're given 20.2 milliliters. From both of these, we can use the molarity formula to calculate moles of our silver ion. We can go moles of silver ion to moles of our chloride ion, and then of course convert back to grams, and that would give us our answer. And so that's what we're going to do here on our next page. So first thing we're going to do is use that molarity formula, and we'll once again solve this for moles. Molarity equals, moles equals molarity times liters, and so we're going to go 0.100 molar multiplied by 20.2 milliliters divided by 1,000 milliliters to convert to liters. Got to make sure we do that. And so we have moles of our silver is equal to 0.0020 moles of silver ions. From there, we're going to use our stoichiometry. So 0.0020 moles of our silver ions, and let's convert that to grams of chloride ion. Okay, and so what we're going to do is we're going to do our mole ratio, so moles of silver to moles of chloride, and that is going to be a 1-to-1 ratio there. Now, all we have to do is calculate our molar mass of our chloride ion, which is going to be the same as the molar mass of chlorine. Remember, electrons are incredibly light. They don't really have much mass, so when you lose an electron to form the chloride ion, or gain an electron to form, let's say, the silver ion, you're really not going to affect the mass, so we can go ahead and use the same exact mass because electrons are so light. So we now have our setup here, and so our answer is going to be left in grams of chloride, and I come out with 0.0716 grams of our chloride present. This would be the type of titration that might be done, let's say, in a water supply, where the city of Atwater would have to take a look at what's dissolved in their water and periodically send out a statement to all the citizens of Atwater. Chloride is chlorine, and chloride is used for various things. And so that would be one way so we could do that in our municipal water. Take a look at the chloride concentration. A little too much chloride concentration combined with a little bit too much sodium concentration, and then we have salty tasting water, which we definitely don't want. Okay, so that's today's lecture, and we'll do some practice problems on these tomorrow in class. Have a nice day.